Okay, let's dive right into this explainer and demystify the complex standardized building code of modern hardware verification. I'm talking, of course, about the Universal Verification Methodology, or UVM. Now, if you've spent any time at all in ASIC or FPGA design, you already know the deal. Verifying the hardware often takes way more time and, honestly, way more code than actually designing the thing in the first place. So today, we're going to break down exactly how UVM structures this massive task. And to make it super relatable, we're going to use a metaphor that's really easy to visualize. We're going to map UVM to building a functioning city. Here's a quick look at our agenda. We'll start with the rise of UVM, then move into synchronizing with UVM phases, TLM component communication, analysis ports and FIFOs, and finally upgrading to UVM resources. Like I said, we'll keep mapping this to building a city, looking at the foundation, the zoning laws, the road networks that move data around, and the city registry. Let's get right into it. Section 1. The rise of UVM, or the foundation of our verification city. You know, every great city needs a rock-solid foundation, right? Well, the verification landscape wasn't always this organized. Before UVM, the verification world was honestly kind of a mess. It was highly fragmented. We had all these competing methodologies that made reusing code across different projects, or especially across different companies, just a massive headache. Looking at this timeline, you can see how the industry essentially shifted away from those vendor-specific libraries and moved toward a unified open-source IEEE standard. Back in 2005, Synopsys gave us the Verification Methodology Manual. Then, around 2007, Cadence and Mentor teamed up for the Open Verification Methodology, which introduced some really cool concepts, like dynamic object overriding. But the real game changer? That was standardizing the whole thing under the IEEE in 2017 and then refining it in 2020. This standardization decoupled verification from proprietary simulators. It didn't just lower costs. It allowed the industry to create a universal factory to effortlessly manufacture and swap out components across the board. Moving on to Section 2, synchronizing with UVM phases, which is essentially our zoning and clocks. Now that our foundation is poured, we need to talk about the timeline. Just like a city has to be zoned and built before people can actually move in and start driving around, a test bench has to be carefully constructed over time so components don't step on each other's toes. In UVM, this synchronization happens through phases, and this strictly separates the setup from the actual action. First, we had these non-time-consuming phases that all happen at simulation time 0. During the build phase, we don't just build components randomly, we register them with the UVM factory. Actually, here's a classic interview question for you. Why do we register every component with the factory and use the typeid.create function instead of just using standard SystemVerilog new constructors? Well, the answer is that the factory exists to give us ultimate flexibility. By using typeid.create, it allows us to instantly swap, say, a basic base driver for an extended error-injecting driver later on, all without rewriting a single line of our core test bench code. It's brilliant. So once they're manufactured top-down, we connect them bottom-up in the connect phase. By the time we hit the run phase, which is the part that actually consumes simulation time, everything is already perfectly in place. And after the run phase wraps up, we go back to zero-time phases like extract and check to evaluate our scoreboard data. But this brings up a really interesting problem. During that time-consuming run phase, tests are executing in parallel across all these different components. So how does the system actually know when everyone is finished and it's time to safely end the simulation? To solve this, UVM uses this fantastic concept called the phase objection mechanism. You can think of it like a collective lock on the simulation clock. If a component knows it needs time to complete a task, it raises an objection right at the start, at 0 nanoseconds. This objection literally prevents the simulation from abruptly moving to the next phase. So, for example, if component A takes 40 nanoseconds to run its test, and component B needs 100 nanoseconds, they both raise an objection. Component A drops its objection at 40 nanoseconds, but the simulation stays in the run phase because component B is still holding its lock. It's only when the very last objection is dropped at 100 nanoseconds that the simulation safely moves on. All right, Section 3, TLM component communication, or the roads and mail system. So our city is zoned and synchronized, but now we need infrastructure. Our components have to talk to each other, but we don't want them rigidly hard-coded together. That brings us to transaction-level modeling, or TLM, which acts as the mailboxes and roads between independent components. Let's look at the three main pieces of this infrastructure. First up is the port.
A TLM port is essentially an outgoing mailbox. It's an object instantiated inside an initiator component, and it defines exactly what interface methods are required, something like a put or a get command. But here's the crucial part, and it's kind of like a puzzle piece. The port only defines the request. It doesn't actually do the work itself. Next, we have the export. Think of an export as a mail forwarding facility in our city. If a parent component has a child component that actually knows how to handle a transaction, the parent uses an export to promote that connection pathway up the hierarchy. It's basically saying, hey, I accept this mail, and I know exactly who down below is going to process it.
And finally, we reach the IMP, which is short for Implementation Port. The IMP is the final desk at the very end of the line. This is where the actual work is physically executed by the target component. If a port initiates a put task, the IMP is the final destination that receives that data and actually does something with it.
Now, what's really cool is how these pieces snap together during that 0 nanosecond connect phase we talked about earlier. Connections route from a child's port up to a parent's port, across to another parent's export, and finally down to a child's IMP. But UVM is incredibly smart here. Right before the simulation begins, these complex hierarchical connections are mathematically resolved into a single, highly optimized hop. So during the actual simulation, calling a ports method jumps directly to the implementation, zero hierarchical overhead.
Section 4. Analysis Ports and FIFOs. Broadcasting data. Okay, so ports and exports are great for point-to-point stuff, like a driver asking a sequencer for the next item. But our city also needs a radio broadcasting system for passive observation. Enter the analysis port. This is a specialized TLM port that operates exactly like a radio tower. It broadcasts read-only transactions to 0, 1, or even 20 connected subscribers simultaneously, all using a single write function. These are absolutely perfect for passive components, think scoreboards or coverage collectors. The component broadcasting the data doesn't block or wait. It just shouts the data into the void, and whoever happens to be tuned in gets a copy. But sometimes, your producer and consumer are operating completely independently. They might even be on totally different simulation clocks. You definitely don't want a fast producer getting blocked by a slow consumer, right? In that case, UVM lets us drop a UVM TLM FIFO right between them. This acts as a buffer. The producer puts transactions into the FIFO, and the consumer independently gets them out whenever it's ready. It safely manages everything without any hierarchical lock-in. Section 5. Upgrading to UVM resources, the city registry. Finally, we need to talk about where global configuration data is stored. And listen up, because there is a massive architectural shift happening right now in how verification engineers handle this. Just look at the tangled mess on the left side here. The traditional UVM config DB rigidly requires a component context and these really complex string paths. It is notoriously frustrating when you're trying to access data from inside a sequence, because it forces you to use those messy p-sequencer workarounds. On the flip side, looking at the right, the underlying UVM resource DB uses straightforward string scoping. It can be accessed from absolutely anywhere, even non-component classes. It truly unlocks architectural freedom. So, you might be wondering, why does almost everyone still use the harder method? Well, here's a bit of an insider secret. As verification expert Cliff Cummings points out, it's basically a historical accident. The config database was actually meant to be just a transitional convenience API for legacy OVM users who were migrating to UVM. It was literally never meant to be the main tool, but because early textbooks printed it, it mistakenly became the industry default. Upgrading your test benches to use UVM resources instead of configs cleans up your architecture immensely. It completely eliminates the need for virtual sequencers just to pass configuration data. It also gives you powerful new tools like retrieving data by its type rather than just its name. And when you pair this with those UVM factory overrides we mentioned earlier, you achieve ultimate flexibility. In a real project, you could use a type override to globally replace all standard packets with error packets for a specific test. Or you could use an instance override to precisely target one specific driver deep in the hierarchy, swapping it with an extended driver, all without touching your base code. And the best part? It's backward compatible. Since both APIs access the exact same underlying UVM registry, you can start using resources for new components today while gradually refactoring your old code. So, taking a step back and looking at our entire verification city, the underlying genius of UVM really becomes clear. Every single mechanism, from the factory manufacturing the buildings, to the strict timeline of the setup phases, the standardized TLM road network, down to the global resource database, is ultimately designed with one goal in mind. It keeps components perfectly isolated yet flawlessly synchronized. It allows you to plug, play, and reuse your verification IP anywhere.
I'll leave you with this thought. Are your current test benches carrying the baggage of legacy habits? Are complex config databases and rigid connections holding back your verification efficiency? Maybe it's time to break free from the old textbook examples, refactor your code, and upgrade your verification city's infrastructure to leverage the full power of UVM.
Thanks for joining me on this explainer, and I'll catch you in the next one.